Hi everyone, welcome back to my YouTube channel. I am Reeti and I am back with another lecture in the DBMS series. So in the last couple of lectures we learned about serializability and concurrency control mechanism. In this particular video we would be learning about types of concurrency control mechanism. So without any further ado, let's get started. So here are some of the commonly used concurrency control mechanism. The first one is log-based protocol. The second one is timestamp based protocols. The third one is optimistic concurrency control, and the fourth one is multi-version concurrency control. So let's start with log-based protocols. So before starting with log-based protocol, let's just revise some older concepts. So in concurrent schedule, there was a non-serial execution happening, and because of this non-serial execution, the consistency was very low. Now for this non-serial execution, we introduced the methods such as serializability and concurrency control mechanism. As part of serializability, we try to see that if a given schedule is serializable or not. As part of concurrency control mechanism, we make the schedule as serializable. So here is the first concurrency control mechanism, that is log-based protocol. So as the name suggests, we are using some kind of logs so that we can achieve serializability and so that we can make a schedule serializable. So here are some types of log. The first log is binary log. So it is a simple mechanism where a data item can either be logged or unlocked. If a thread tries to acquire the lock when it's already locked, it must wait until the lock is released by the thread currently holding it. So as part of binary lock, we can lock or unlock a given data item A. Now coming to the next log, that is shared and exclusive log. So in shared log, it allows multiple transactions to read a data item simultaneously but prevents any of them from modifying it. So whenever we want to perform a read operation on any data item, we can use a shared log, but we can't do any modification. Multiple transactions can hold shared log on the same data item at the same time. So since it is used for the read operation, and whenever there is a read happening in different transactions, there is no conflicts. So multiple transactions can hold a shared log on a same data item. Now coming to exclusive log. So it allows a transaction to both read and modify a data item. When an exclusive log is held by a transaction, no other transaction can read or modify the data item. So whenever we want to perform a read as well as write operation on a data item, we can use an exclusive log. Now whenever we are using an exclusive log in one of the transaction, in next transaction we can't use the exclusive log on the same data item because there might be some read as well as write conflicts. So in shared log, we are using it for read purpose, and exclusive log we are using it for read as well as write purpose. So whenever there is a write operation involved, there might be some conflicts such as write read conflict, write write conflict, and read write conflict. So just to avoid all these conflicts, if there is one transaction which is acquiring a exclusive log, we don't provide exclusive log to the next transaction. So if there are two transactions T1 and T2, and T1 is having an exclusive log, when T1 unlocks that particular exclusive log, we can assign an exclusive log to T2 for the same data item. So when it is unlocked, we can go ahead and assign the log. But in shared log, if transaction T1 is having a shared log on a data item A, as part of T2 also we can assign a shared log on data item A, because there is a read operation, so there is no conflict. But here, since write operation is involved, there could be read write read conflicts. So here you can see that there are two transactions T1 and T2. As part of T1, we are giving an exclusive log, we are performing a read operation on A, write operation on A, and then we are unlocking it. After that, we are providing a shared log on B. So here you can see that there are different data items. So if there are different data items, we don't need to wait for one particular exclusive log to unlock or release itself. We can provide any shared or exclusive log to different data item. It is only applicable when the data item is same. So whenever there is a same data item, we can say that there could be some conflicts, but when the data item are different, there won't be any conflicts. So here we have provided a shared log, we are reading the value of B, and then we are unlocking it. So when we unlock any log, we can go ahead and provide any shared or exclusive log in case of an exclusive log. So when a transaction acquires a shared log on a data item, other transaction can also acquire a shared log on the same data item. So if there are two transactions T1 and T2, and T1 is acquiring a shared log, as part of T2 we can again acquire a shared log, enabling concurrent reads. However, no transaction can acquire an exclusive log on the data item as long as one or more shared logs are held. So if there are two transactions T1 and T2, as part of T1, if I am giving a shared log on A, I can't provide any exclusive log on A as part of T2 until this particular lock unlock itself. Because again, as part of exclusive lock, I am doing a read as well as write operation, and as part of shared lock, I am doing a read operation. So there could be a read-write conflict which could occur. So there will be a RW conflict. Now, when a transaction acquires an exclusive lock on the data item, it has full control over the item, meaning it can read and modify it. No other transaction can acquire a lock on the same data item until its exclusive lock has been released. So if there are two transactions T1 and T2, and if T1 is acquiring an exclusive lock on A, T2 can't acquire an exclusive lock on A until or unless this particular lock is unlocked. So if there is an exclusive lock involved, there won't be any shared lock or exclusive lock, and if there is a shared lock, then there won't be any exclusive lock. There can only be a shared lock. So when there is a shared lock, there can be only shared lock, no exclusive lock. When there is an exclusive lock, there can't be any shared or exclusive locks. So shared lock can be present in any number of transactions. For exclusive lock, only one transaction should hold it at one time. So while shared and exclusive locks are vital for maintaining data integrity and consistency in concurrent environments, they can also introduce significant challenges in terms of performance, deadlocks, reduced concurrency, and system complexity. So although they are helping us to achieve serializability to some extent, but there are some issues such as deadlock, reduced concurrency, and system complexity. Now, what are the drawbacks of shared and exclusive lock? So the very first one is performance issue. Managing lock require additional CPU and memory resources. The process of acquiring, releasing, and managing locks can introduce significant overhead. So here we are acquiring a lock of exclusive or shared, and then we are releasing that particular lock. So it can introduce some performance overhead, because of which the performance issues can arise in our CPU as well as in our memory. Now coming to the next pointer, that is concurrency issues. So exclusive lock prevent other transaction from accessing locked data item, which can significantly reduce concurrency. So in concurrency, what we say is, if there are two transactions T1 and T2, there could be some interleaved transaction which is happening. But if I am acquiring an exclusive lock on any one of the operation of the transaction, other transaction can't go ahead and access the same data item until or unless the lock is released. So coming to the next point, that is starvation. Some transaction may be delayed if higher priority transaction consistently acquire locks before them, leading to starvation where a transaction never gets to proceed. Consider if there are three transactions T1, T2 and T3. As part of T1, I am acquiring an exclusive lock. It is happening at time T. As part of T2, I am acquiring a shared lock. It is happening at time T dash. And as part of T3, again I am acquiring a shared lock, which is happening at point T double dash. So here you can see that we are acquiring locks in different transactions, but since in transaction T1 there is an exclusive lock and this lock isn't released yet, so there won't be any lock which would be acquired in T2 and T3, and they will wait for T1 to complete. Consider that T1 completes at time T double dash. There is an unlock happened at time T double dash, and here shared lock on A is being demanded. So it will go ahead and give that particular lock to T3. It will say that your wait time is over, now you can acquire a lock. But T2 was waiting from the long to get the lock for itself, but it is now again waiting because there are some more higher priority operations which are coming into picture. This is how starvation happens in transaction, when transaction may be delayed if higher priority transaction consistently acquire locks. Now coming to deadlocks. So shared and exclusive lock can lead to deadlocks where two or more transactions hold locks that other transaction need. So there could be some deadlocks which could be formed, because consider if there are two transactions T1 and T2, where T1 is acquiring an exclusive lock on A. Now T2 comes in, acquire an exclusive lock on B. This could happen because the data item are different. Now again T1 wants an exclusive lock on B. So it needs to wait for T2 to get completed, and consider that T2 again want an exclusive lock on A. So it needs for T1 to get completed. So here you can see that there is a loop which is getting formed and none of the transaction is ever completing and they are waiting for themselves. So because of this, the deadlock issue happens. We'll be learning about deadlocks in more depth in next set of slides. Now coming to the next point, that is irrecoverable. So if transaction B commits after the lock is released based on a modified value in transaction A which fails after some time. So consider if there are two transactions T1 and T2. As part of T1, I am giving an exclusive lock on A. I am reading the value of A. I am modifying the value of A. And then I am unlocking A. As part of T2, again I am giving an exclusive lock on A. I am reading the value of A. And I am writing the value of A. And then I am unlocking it. Consider that this particular transaction T2 goes ahead and commit all the changes in the database. Now in the database all the changes have been committed and it has read the updated value here, and on basis of that updated value it has performed the write operation. But consider that at some point this particular transaction fails, because nowhere we have told that there would be unlock happening when the transaction has committed all the changes. We haven't said that. So there could be a chances that there is some failure which has happened at some point of this particular transaction. So it will roll back all the operation and all the changes which was done as part of this transaction, but this particular transaction has read the value which was modified as part of T1, but now T2 is having an invalid value and that is already updated in our database. So this particular transaction can be recovered, but this particular transaction can't be recovered. So there is irrecoverability. Now what is this deadlock? So it is a situation when two or more transactions wait for one another to give up the locks. So here you can see that there is a resource R1 which is assigned to a process P1. Now P1 is waiting for R2 and R2 is assigned to P2 which is waiting for R1. So here you can see that there is a loop which is getting formed because P1 is dependent on R2, R2 is dependent on P2, P2 is dependent on R1 and R1 is dependent on P1. So there is a loop and there is a deadlock which is getting formed. So we saw that in the shared and exclusive lock there were some drawbacks. So because of this we introduced the two-phase locking. Now what is this two-phase locking protocol? This protocol ensures serializability by dividing the execution of a transaction into two distinct phases. First one is a growing phase. A transaction can only acquire locks but cannot release any. This phase continues until the transaction has obtained all the lock it needs. And coming to the shrinking phase, so after the transaction releases its first lock, it can no longer acquire any new locks. During this phase the transaction releases all the locks. So there are two phases, growing phase and shrinking phase. In growing phase they can go ahead and acquire any kind of lock they want, and in shrinking phase they have to unlock all the locks and they can't acquire any lock. So because of which the transaction can achieve serializability and consistency in the given schedule. So let's see how it happens. So here are two transactions T1 and T2. As part of T1 we are acquiring an exclusive lock on A. So we can say that T1 is right now in a growing phase. So it is going in a growing phase, so there is a read of A, write of A happening. Now transaction T2 comes, but since T1 is right now in a growing phase and T2 is not in a growing phase, there won't be any locks which would be assigned to T2. It will wait for this one to have in a shrinking phase and unlock all the locks. Now coming to here, there is a shared lock acquired on B, there is a read on B. So till here there is a growing phase which is happening because all the operations of the transaction are only acquiring the locks. Now there is a unlock of A which is happening, which is for this exclusive lock, and then there is a unlock of B which is happening, which is for this particular shared lock. So this particular state we can call as shrinking phase, and this particular phase we can call as growing phase. So now there is a growing phase of T1 and then there is a shrinking phase of T1, and since the shrinking phase of T1 is achieved, we can go ahead and acquire a shared lock on A present here because right now it is unlocked. So you can see that when a transaction acquires a growing phase, it will go ahead and acquire locks in that particular growing phase. It won't go to another transaction and give any kind of locks until or unless there is a shrinking phase which has happened for all the locks which is present here, and then they can go ahead and give the shared lock or exclusive lock in another transaction which are waiting for them to get completed. So in this way we can achieve the serializability and consistency, because here you can see that first all the operation of transaction T1 is getting completed, only then the T2 one is starting. So T1 is getting completed first and then the T2 is starting. So there is a serializability which is achieved here. Now let's see the advantages and disadvantages of 2PL, that is two-phase locking. So first one is it guarantees that the schedule of transaction will be serializable, meaning the results of executing transaction concurrently will be the same way as they were executed in some serial order. So if there are two transactions T1 and T2 and there are some operation which is happening concurrently, consider read of A, write of A in T1, then there is a read of A in T2, then there is a read of B in T1, and then there is a write of B in T1. So as part of 2PL, there will be two phases, growing phase and shrinking phase. So first it will start with the growing phase. It will acquire an exclusive lock on A. There will be one more exclusive lock on B. So it will acquire all the locks in the growing phase. Now there will be a shrinking phase where it will unlock all the locks. So it will unlock A and it will unlock B. But since T2 has a read operation, it will wait for this particular exclusive lock to get released. Only then it can acquire a lock. So the shared lock on A in T2 will wait for this particular exclusive lock on A to get completed or get unlocked. Only then the transaction of T2 will start. So here you can see first the transaction of T1 is getting completed, then only T2 is getting started. So there is a serial execution which is established. So there is a serializability. Now by ensuring that the transaction are serializable, 2PL helps to maintain data integrity and consistency, which is critical in environments where data accuracy is essential. Now coming to disadvantages, deadlocks, starvation and cascading rollbacks are still there. So consider if there are 3 transactions T1, T2 and T3. As part of T1 we are acquiring an exclusive lock on A, as part of T2 we are acquiring an exclusive lock on A, and as part of T3 we are acquiring a shared lock on A. Now consider that this particular has come to its shrinking phase and there is an unlock which has happened. So this one was waiting for this unlock to happen so that it can acquire an exclusive lock, and this was waiting for this one to complete so that it can acquire a shared lock. Now consider at some moment of time this particular transaction fails. So it will go ahead and roll back this particular transaction, but since this and this transaction was dependent on the changes which was done as part of T1, so this will also go ahead and roll back, and this will also go ahead and roll back. So there will be a cascading rollback which would be happening because one of the transaction has failed, another transaction had some dependency on this particular transaction T1. Now transaction must wait for the locks to be released by other transaction. This can lead to increased waiting time and lower the system throughput. So here you can see that as part of T2 we wanted to do a read operation, but we need to wait for all the exclusive locks and shared locks which has been assigned in this transaction to get released so that we can acquire any locks and we can proceed with our transaction. So here you can see that the waiting time is more. Now coming to the third one, in case of a system failure, recovering from a crash can be complex, because consider that if at some point this particular transaction failed and this particular transaction was dependent on some of the values which is present in this transaction, so we can't go ahead and roll back the committed changes which we have done as part of other transactions. So in shared and exclusive lock, there were a couple of disadvantages which is taken care in two-phase locking, like serializability is achieved here, concurrency is achieved here, data integrity is achieved here. But there were some disadvantages like irrecoverability, starvation, deadlocks, and cascading aborts which is newly introduced is still persisting here. So for this we have a stricter version of 2PL, that is strict two-phase locking. So what is this strict two-phase locking? A stricter variant where exclusive locks are held until the transaction commits or aborts. So as part of exclusive lock we do a read as well as write operation, and as part of shared lock we only do a read operation. So what was happening is, consider in one transaction there is an exclusive lock which is present, there will be a write operation which would be present, and because of this write operation, if another transaction is reading anything which is modified here, and what if this fails, there will be an invalid update into our database. So because of which it says that the exclusive locks are held until the transaction commits or abort. So this particular transaction should commit or abort, only then the unlock of this particular exclusive lock would be happening, so that if there is any modification which is made as part of a transaction T1, T2 shouldn't read any invalid value. If it's a commit, it will go ahead and read the valid value which is present in the database. If this is a abort, it will go ahead and roll back to its original value. So at this case there won't be any dirty read problems which would be happening. So this helps prevents cascading rollbacks, where one transaction rollback causes other transactions to roll back. So here we are only unlocking it or releasing the lock once the transaction is committed or aborted. So there won't be any cascading rollbacks which would be happening in different transactions, because there were no strict rules for any of the lock that when they can unlock themselves. But as part of strict 2PL, we says that if there is any exclusive lock, it would only unlock itself once it commits or abort its operation. So the advantages are it prevents the cascading aborts. The second advantage is it ensures strict serializability. So there will be a strict serializability which would be ensured, because there won't be any invalid data which is getting updated in our database. So the consistency is more here. Now coming to the disadvantages. So since write locks are held until the end of transaction, other transaction may be blocked for extended periods. So since there is an exclusive lock which is happening in transaction T1, it will only unlock itself once it commit all the changes in the database. So there might be some time which should be taken by transaction T1 to commit all the changes. Till then T2 would be waiting for a shared lock which needs to be acquired only when the T1 is unlocking the lock. So once T1 is unlocking the lock, only then T2 can acquire a shared lock, so the wait time will be more. Now coming to the next point, that is transaction may experience longer wait time to acquire the locks. So transaction may experience some longer wait time to acquire the locks. Now the third one is deadlocks and starvation is still there. So deadlock and starvation is still not encountered as part of strict 2PL, because again consider as part of T1 we are having an exclusive lock, as part of T2 we are having a shared lock, as part of T3 again we are having an exclusive lock, as part of T4 again we are having a shared locks. So these all locks needs to wait on each other to unlock, so so that they can start their execution. So there still be deadlock which would be happening and a loop which would be happening, because all the other transactions are interdependent on each other for them to be unlocked. So here we can see that again there are some disadvantages which are still persisting. So there is one more stricter version of strict two-phase PL, that is rigorous two-phase PL. So what is this rigorous two-phase locking? So it is an even stricter version where all the locks, shared and exclusive, are held until the transaction commits. So 2PL, it says that the exclusive lock should only unlock themselves when they have committed or aborted the changes. But as part of rigorous 2PL, it says that exclusive lock as well as shared lock should commit or abort the changes, only then they can go ahead and unlock themselves. So the lock are held until the transaction commits or aborts. Now what are the advantages? Since all the locks are held until the end of transaction, the system can easily ensure that the transaction are serialized and can be recovered. So since there are locks which is getting held in both exclusive as well as shared lock, so there is a guarantee of serializability as well as recoverability. Now it prevents the cascading aborts and dirty reads. What are the disadvantages? So the performance bottlenecks are there. Increased transaction duration, because earlier they were only hold on the exclusive lock, but now the hold is present on the exclusive as well as shared lock until or unless they commit or abort. So there is an increased transaction duration. Third point is deadlock and starvation is there. So we can see that deadlock and starvation is something which is getting persisted for all the 2PL, two-phase locking, strict two-phase locking, rigorous two-phase locking. So again there is one more locking protocol, that is conservating two-phase locking. So conservative two-phase locking, or you can say static two-phase locking, is a variant of a standard two-phase protocol that aims to prevent deadlocks entirely by requiring a transaction to acquire all the lock it needs before it begins its execution. So what it says that all the transactions should acquire all the locks before even the transaction starts its execution. So if the transaction is unable to acquire all the required locks because some are already held by other transaction, it wait and retries. The transaction only starts execution once it has successfully acquired all the necessary locks. So once a given transaction has acquired all the locks which is needed as part of an operation which is present in the transaction, only then it will start its execution. Until or unless then it won't start its execution and it will wait. So consider if there are two transactions T1 and T2. As part of T1 we are doing a read operation on A, write operation on A. As part of T2 we are doing a read operation on B, write operation on B. As part of T1 again we are doing a read operation on A, write operation on A. As part of T2 we are doing a read operation on B and write operation on B. So before even the transaction start executing, it will acquire all the locks. So here it will need an exclusive lock on A. It will need an exclusive lock on B. So before the transaction start, it will acquire all the locks. So here T1 has acquired exclusive lock on A and exclusive lock on B. So since T1 has acquired the exclusive lock on A and exclusive lock on B, T2 can't go ahead and acquire any exclusive lock because T1 has already acquired all the locks which is needed for T2. And T2 can't start its execution even if one of the lock which is needed by T2 is not present, right? So first T1 will start all its execution, only then T2 can go ahead and acquire any locks and start its execution. So because of this, there won't be any deadlock scenario which would be present, because since a transaction never starts executing until it has all the lock it needs, deadlock cannot occur because no transaction will ever hold some locks and wait for other. So here T2 won't be holding any locks, even though it requires an exclusive lock on A and exclusive lock on B. It needs to wait for this particular transaction to get completed. Only then T2 can go ahead and start its execution and acquire the lock. Here T2 has not even started its execution, then how it can go ahead and acquire a lock, right? So there won't be any deadlock situation which would be present here because T2 can't acquire any lock because all the locks have been acquired by T1 and it needs to wait for them. So in this scenario, deadlock cannot occur because neither T1 nor T2 starts its execution until it has all the lock it needs. Now coming to the next concurrency control technique, that is timestamp based protocol. So it assigns a unique timestamp. So whenever there are two transactions T1 and T2 and they start at any instant T, or you can say T dash, so it gives a unique timestamp to the transaction whenever they start its execution or their operations. So every transaction is assigned a unique timestamp when it enters the system system, it is used to order the transaction based on their timestamp. So we can order the transaction that T1 started first, then T2 started, or we can also order their operation that read of A started of T1 first, then read of A of T2 started. So all these operation and all these transaction we can give a timestamp. So there are two important timestamps for each data item. First one is read timestamp, second one is write timestamp. So the last timestamp of any transaction that has successfully read the data item, that is RTS. So consider if there are two transactions T1 and T2. As part of T1 I am reading a value of A, writing a value of A. As part of T2 I am reading a value of A. So the last read operation on data item A happened on T2. So we can say that the last read operation happened in transaction T2 at particular timestamp T dash. So that is the RTS. Now coming to WTS, consider that it is doing a update on A, and here also it is doing a update on A. So we can see that the last update on A has happened in T2 at timestamp, you can say T double dash. So WTS of this is T double dash and RTS of this is T dash. So we give the latest of the read and the latest of the write timestamp. Now transaction with smaller timestamp are called as old transaction. Transaction with larger timestamp are called as young transaction, because consider that if there are two transactions T1 and T2, now T1 started at 7 p.m. and T2 started at 7:10 p.m. So we can say that this particular one would be having a larger timestamp and it would be having a smaller timestamp. So we can say that this particular transaction is an old transaction and this particular transaction is a young, or you can say a fresh transaction. Here are some rules for the timestamp based protocols which help us to tell that if there is a transaction, as part of that transaction if there are any operation, that should be executed or that should be rejected. So here is a RTS, that is read timestamp of A, WTS, that is write timestamp of A. So consider if the transactions are getting performed on a data item A. So first one is check the following condition whenever a transaction Ti issues a read operation. So whenever there is a read operation which is issued by a transaction Ti, what should we check? So first one is the write timestamp of A should be greater than the timestamp of Ti, then the operation is rejected, that is rollback. If the write timestamp of A is less than or equal to the timestamp of Ti, then the operation is executed and we set the read timestamp of A as the maximum of read timestamp of A and the timestamp of transaction Ti. Now coming to the second pointer, check the following condition when the transaction Ti issues a write operation. So the first one is if the transaction Ti is less than the read timestamp of A, then the operation is rejected, that is roll back the transaction Ti. If transaction of Ti is less than the write timestamp of A, then the operation is rejected and Ti is rolled back, otherwise the operation is executed and we set the write timestamp of A to timestamp of Ti. Now again I know that this particular rules would be sounding very confusing to you. You won't be even understanding that what is happening here. So I'll just give you a small trick which you can keep in mind so that you can know that if there are two transactions T1 and T2, then what all operations should be executed or rejected. So I told you about old and young transaction, how we distinguish between old and young transactions. So consider if there are two transactions T1 and T2, and if the timestamp of T1 is less than the timestamp of T2, we can say that T1 is an old transaction and T2 is a young transaction. Now consider if as part of T1 and T2 we are performing some operation. So since T1 is an old transaction, we assume that T1 should be completed first, only then T2 should be completed. So there would be a serial execution that T1 should be completed first, only then T2 should be completed. Now consider that as part of T1 I am doing some operations and as part of T2 also I am doing some operations. So here there are no issues because T1 is getting completed first, only then T2 is getting completed. But consider if there is a use case where T2 operation is starting first and then after T1 operation either read operation or write operation is happening, although T2 started at a later point. So whenever the older one has done all the operations and then younger one has started its operation and older one is getting completed, there is no issues. But when the younger one has done all the operations and then older one comes ahead and does some of the operations, then there would be a rollback. So let's assume that there are two transactions T1 and T2. Suppose the transaction T1 has entered the system at 7 p.m. and transaction T2 has entered the system at 7:05. So T1 is the old transaction and T2 is the young transaction. Now then T1 has a higher priority, so it executes first and it enters the system first. So T1 will be executing first and then T2 would be executing. So it will be T1 goes to T2, that is a serial execution where T1 operations is completed and then T2 operation is getting completed. So how we can see that if there would be any rollbacks which would be happening? So if the younger one has done a read or write operation, so younger one has done a read or write operation and older one wants to do a read or write operation, then that is a rollback case. If younger one has done any read or write operation and older one wants to do any read or write, so there should be a rollback. So you can just remember in this way that if younger one is performing any operation and then the older one comes in and perform any of the operation, there should be a rollback. But if older one is performing any operation and then younger ones come, then there is a no rollback. So here you can see that there are two transactions, T1 and T2. T1 is old, T2 is younger. So T1 is performing operation, T2 is performing operation, no issues. T1 is performing a write operation, T2 is performing a read operation, no issues. T1 is performing a write operation, T2 is performing a write operation, no issues. Because we are expecting that T1 would be completed first as it has entered the system first, and on the basis of priority, T1 should be completed. So this is how this timestamp based protocol works. So you just need to remember that if the younger one does some transaction and after that the older one comes ahead and does some transaction, they should roll back. But if the older one is doing any transaction and after that the younger one is doing, there shouldn't be any rollback cases. So this is all about the concurrency control mechanism. I hope you like this video. So if you like this video, please hit the like button. If you're someone who is new to my channel, can go ahead and watch out the tech content first, and if you find it useful, can go ahead and subscribe. Also, if you have not followed me on my social media handles, you can go ahead and follow. The links are in the description. Till then, take care, keep learning, keep growing, keep smiling. Bye all.